All right, so what we were doing last time, um, so we were taking a look at this two-dimensional plane stress problem. You have a square plate, and you have a edge traction that you have applied on both these edges, and both these edges are roller or on a roller support. So this is also a problem that I assigned to you on your homework. Um, so the idea here is to divide this into two parts using symmetry, and then you can solve this bottom part by using four triangles, CST triangles. So we already went over most of the formulation the previous time, but there was one thing that we were talking about, how to find out all these, how to find out the shape functions for any element, and you will see that these element matrices turn out to be the same for all these four elements. And after that, all that you have to do is to assemble them and assemble them into a global stiffness matrix and solve that. So last time we were taking a look at what do you do if you want to solve or if you want to enforce the boundary condition on an inclined plane. Thank you. So we said that in order to enforce the condition that we want to enforce the condition that there should not be any displacement in this direction. So what we need to do is to pick out those specific degrees of freedom from the global displacement vector. You pick out those those specific degrees of freedom, transform them, and you will get 5' and 6' on the global coordinates. Okay. And the same thing for 11 and 12, you will get 11 and 12 prime. The rest of the entire matrix is 1 on the diagonal, and everything else is 0. Okay? So this is called a transformation matrix, but you just cannot add or multiply a transformation matrix to your global deformation vector. So if you multiply this T in between here, then you have to also multiply a T transpose. That's right here. So you multiply this T and T transpose, that goes to identity, and if you multiply the whole equation by T, then you will see that this equation is exactly equal to this equation. So finally, in these coordinates, you can go ahead and enforce your boundary condition that 6' is 0 and 12' is 0, and the other boundary conditions we already said were 1, 2 are 0, 4 is gone, 8 is gone. So how many degrees of freedom will we have left in this after you enforce all of these boundary conditions? Six, which would be 3, 4, 5', 9 and 10, and 11', right? So, sorry, 11', that's along there. So that you already know how to do. You pick out the 3 degrees of freedom and you solve them. Okay. Any questions on this setup? Okay. So what I'm going to do today is go over a little bit about the code that I've assigned to you for homework 5. So let's take a look at the input data file that I've given to you. So the idea is that in this code, the first couple of lines will define a material. Okay, so I'm defining a material number 1, and I'm saying that this material is of type plane stress. The Young's modulus and the Poisson's ratio are given to you. In general, you can also have many different materials. You can have material 1, 2, 3, whatever, and it need not even be just elasticity. So we are trying to set up the problem in such a way so that later on we can add to the code and make it more general. Then the next couple of lines tell you that some of the mesh parameters, total number of nodes is 12, and total number of elements is 10. So these are the 12 nodes in this case. This is the smallest mesh that I'm talking about. You have the X, Y locations of all those nodes. You have element data. So This element data is also a little bit different than from what you had in the one-dimensional case. You have all these element numbers. I'm saying that the element is of type T3, which means three-noded triangle. And what we're saying is that each of those elements is of material type 1. So this was the first was the element number right here, element type T3, material number 1. And then we are saying that the body force that is acting on this element is this in the x direction, this in the y direction. So there are 10 elements. Each element can have some body force. Okay. So we are associating the body force not with the global problem, but with each element. Okay. And then finally we have the three connectivities. So what does this connectivity mean? It means that node 1, node 4, and node 2 are connected in an anti-clockwise, counterclockwise manner. Okay. So, and finally we have some displacement boundary conditions. And in this case, we can also apply edge tractions on the entire domain. But in this case, I have not specified any edge traction. So there's no data between this and the nodal loads. We are saying that there are only two nodal loads on nodes 11 and 12. So let's take a look at what this file looks like. And I've also mentioned to you, I think on the discussion, that if you go to all these files, this is 2D FE is the main code, and wherever in the main code I have left these blanks, you can just comment them out, and that will allow you to be able to run it using the Matlab debugger. So all those blank lines have been commented out. So let's take a look at how this code runs. So I'm going to place a breakpoint right here. This is the command that gets the input from the file that I was just showing you. So if I run it now, it's asking me for the name of the input file. This is the input file that I want. And now I'll try to see how this subroutine works. So I'll go into this. I want to step into the routine, and the first couple of in this material routine, this is the get input routine. You read all the data, and I've made some changes to this, so I'll post the newer version of this get input data also. Although it shouldn't make a difference, but still you can work with the latest one. So you get all that material data, and at this point you should have all the mesh nodes. So let me place a breakpoint here and go until this point. So you can see that if you double click on materials, you can see that the material that I had defined has been read in. This is plane strain, this is the Young's modulus, this is the Poisson's ratio, and this type of a data structure in Matlab is called a structure. Has anybody worked with structures in Matlab before? Any other programming language? The idea is that you can collect data that belongs to a certain material and collect all that data in one place, so that you don't have multiple different arrays floating around. So what I'm saying here is that this is material 1. Its type is plane stress, its type, its Young's modulus, and new are these. Okay, so this allows you to write a modular code, meaning that you do not want to have all these global variables floating all over the place. You want to give data to a certain subroutine, only that data that it needs, and you get out whatever output that it generates. Okay, so at this stage in the editor, the next couple of lines, they are for reading the nodes, and let's place a breakpoint here and go up till here. So if you click on nodes, you can see that these are the XY locations of the nodes. Then the next couple of lines are for elements, and this element data structure is a little more elaborate. So if you go to your handout, I've just told you that this material has 3 types of data in it. This nodes is this kind of a vector which has XY values. This element is a more elaborate structure, where the first component of that element is the type of that element, material number, the body force, the connectivities, the three connectivities, and finally there is also a variable that stores any edge loads that are acting on this element. So for example, if this is your element, your body force could be pointing in some general direction. That's why you have Bx and By. Your traction at the edge of the element, that could also have a component in the X and the Y. So you have two components for the tractions. Um, so we've already talked about if we have only self weight, dead weight, then usually By is minus rho times G, and Bx is 0. So can anybody think of a case or scenario where you would have Bx, where what kind of a problem uh, would you have a body force in the X direction? Right. So if you have a rotating body, and if you could have a body force that is a centrifugal acceleration that is acting radially outwards. So that would be a body force in addition to the vertical. Another case is if you have a metallic structure, a steel plate, let's say, and if you are applying some sort of a magnetic field uh, in the horizontal direction, then this steel plate would get attracted uh, to the right, and that would also be a body force. Okay. So these are the types of forces that you would have for each element. These are the different types of data that we are using. So let me go back to the code, and after you read in all the data, what does that look like? So at this stage, we have read all the element data, and if you go and click on this elements, you will see that there are 12 or 10 elements in this case. And if you double click on one of those, it tells you that this is element number 1, which is type T3, material number 1. These are the body forces, 0 and 0. This is the connectivity of that matrix, and the edge loads we have not yet defined. So that is an empty matrix. Okay. So finally, if once this once this input routine finishes, it will read all the data, and let me see if we can go out here. So after the input routine is done, all that you have in the data structure are these values, which are right here in your workspace. So does anybody use Workspace and Debugger in Matlab? Okay. So this is a very convenient way to debug your programs and to make sure how you understand how the program is working. So at this stage, you have all these input data, and finally, we will plot the input to see what it looks like. So, so this is what it looks like, and for some reason, let me say that okay, so this is the mesh that I had assigned for the first part. So you have these 12 nodes, 10 elements, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements, and it's a pretty regular mesh, but you will see that you will not get good results from this mesh. So going back to this, and let me now run it up to here, and let's say input is okay. At this stage, I will initialize the global stiffness matrix. So what do we need to do? We have obtained the input. Now we will try to calculate the local stiffness matrices and assemble them into the global stiffness matrix. Okay. So to do that, we initialize a global stiffness matrix, and if you remember, in the one-dimensional case, we were using zeros. So we were making a matrix of all zeros of the total number of nodes. But in this case, we are going to use a new type of a zero matrix, which is also called a sparse. So the benefit of this sparse matrix is that it does not store the entire square matrix, which would be a huge matrix. So the benefit of sparse is that it allows you to calculate all these quantities in a faster manner. So that's why we are using a sparse matrix in this case, and the dimensions would be twice the nodes, comma twice the nodes, because each node has 2 degrees of freedom. This is your force vector. And finally, if you go in, you have to calculate the stiffness matrix for each element. So we have to run a loop that goes over all the number of elements, calculate the local node numbers, local coordinates, get the D matrix for your material type. So this D matrix is nothing but let's see. So this is all the code for D matrix. What we are saying is, give me the material number. I will give you that 2-dimensional D matrix, that 2-dimensional elasticity matrix. Okay. So once you have the D matrix, you can pass that to your element subroutine. So it checks if it is of type T3, then it will try to calculate its element stiffness matrix. And this is the one that you have to code. Okay. So if you go into this, you'll see that I've given you all the data that this subroutine needs. And actually, you don't need to worry too much about how all the structures are stored and all that. You just have to code, you have to understand that what is the input that is coming to this subroutine and what is the output that you need to produce. So in this case, you know that the input is going to be this 3x2 matrix of nodal coordinates of the element. Once you have the nodal coordinates x1, x2, x3, we know how to calculate shape functions, we know how to calculate B matrix, we know how to calculate K matrix, and so on. So that is what you have to code here. Okay, and after that, it goes back to the main, and you see that I've left empty lines in here for later on when we include more types of elements. Okay, and this is fine. The Matlab will not complain about having empty lines in here. So, all right. So let me stop the debugger here, and let me show you what the sample output looks like. Okay. All right. So for the first type of problem, we say that the input is fine. Okay, and these are the 3 stress plots that your code should produce. So you can see that this is a constant strain, constant stress triangle. So the stress within each element is pretty much constant. And this is the stress in the XX direction. So this is the XX direction, in the YY direction, and the shear stresses in the XY direction. So let's say we want the average stresses, and what averaging does is you are going, for example, for this node, you are going to calculate the stresses that are averaged from all these neighboring elements. So if you do that, then the stress profile gets much smoother. But still, you can see that the displacement that you get at the tip is barely 0.05 or something. And both these nodes are constrained in the X and the Y, so that is also not a good boundary condition to use. So if you use the next finer mesh, what happens? So the next mesh has 40 elements. So let's say you can see that a lot more elements, but obviously you don't have to do anything. I've provided this mesh. You just have to run the code. Let's say the input is okay, and again you see that each of those triangles has a constant stress state if you don't average it. Now if you say you want to average it, then you start to see that the displacement has gone up quite a bit, and the stresses are more or less smooth. So fine. There are a couple of other refined meshes. There's one with 160 elements, and there are two others with 640 and 2,560 elements. So this mesh, let me show you the final one. So obviously there's lots and lots of triangles and lots of nodes and elements. Another point to make here is that this mesh you would not be able to solve with your Abacus student version, because Abacus student version is limited to 1,000 nodes, and this mesh has more than 1,000 nodes. Okay, so let's say the input is okay, and you can still see that even for such a big mesh, it was able to calculate the answer like that. So it's pretty fast. Okay, and the stress profile, even though we have not averaged it yet, is pretty smooth. But after you average it, it becomes much smoother. And this is very close to what you would get from the exact solution. You can compare it with the exact solution also. All right. So any questions on the code structure? I guess you'll have to take a look at the code and see how it is working. But just to point out a couple of things here. Once you have this element stiffness matrix, all that you need to do is to assemble that, and to assemble that you would have to form this element degrees of freedom vector. This is very similar to your one-dimensional or the truss problem vector. You would have to add all these nodal loads. So for example, in this case, these are the two nodal loads, and let me show you for the biggest mesh, what do these nodal loads look like. So this is the 2,500. There are these many nodes, these many elements. You have to go way down here to see that there are actually 17 boundary conditions, and the boundary conditions are also denoted a little in a specific way. So for example, here, what this first line is saying is that node number 1 is constrained in the x direction, but it is free in the y direction. So this can be 0 or 1, this can be 0 or 1. Okay. What we're saying is that this is constrained only in the x direction, it is free to move in the y direction, and it is constrained in the x direction by amount x, which is equal to 0. So if you wanted to specify that it has a specific displacement, you can do that here. Okay. And you can see that there is only one node, which is node number 9, which is constrained in both the x and the y direction. And we have to have that because otherwise the whole beam will move up and down vertically. Okay. And finally, these are the nodal loads that you have for this biggest mesh. Each of these nodes has to have these forces directly applied to the node. So all the x forces are 0, all the y forces are given here. So essentially what this means is that on that beam we have a traction or nodal loads applied on the right edge. So that's what these input files mean. And so those are the nodal loads that you need to add here. And here is another a little bit more involved part. You would have to calculate which are the degrees of freedom which are specified, which are the degrees of freedom which are free. So basically what I'm asking you to do is to calculate these two vectors. These two vectors are the same type of vectors that you've used for your truss problem, for your one-dimensional problem. And finally, the solve step is very simple. To find the degrees of freedom of the free nodes, you just have to not explicitly inverse, but do a Gaussian elimination. So this backslash actually solves the matrix system of equations without explicitly inverting the matrix. Once you've found your D free, you can find your reaction forces, which is right here, one line each. That's your solve. And after that, it's all post computation. So in post computation, you need to find the new location of the nodes, and I'm saying that you can find the new location as old location plus some magnification times the solution that you've just calculated. So did anybody take a look at this for the truss problem? The reason that we have to go and do this reshape and all that is because this vector is a 2 times number of nodes length of vector, and this is a number of nodes cross 2 matrix. So after that, you can calculate the stresses within each element. So again, you have to go back into the loop for each element. You have to calculate all the stresses. But anyway, all that is already done for you, so you don't need to worry about that. You just have to worry about the element routine and assembly and boundary conditions. Okay? And take a look at how this averaging is being done also in the code, because that's a similar procedure you will need later on for Q4. Okay? Any questions? All right. So back to the handout. This is what we just talked about. So the overall flow of the code is get input, loop over the elements to form these, assemble, enforce boundary conditions. These are the 2 lines to solve for D, and finally plot these results. All right, so today what we are going to do is to talk about a general Q4 element. This is something that we introduced last time about a rectangular or a square element. But obviously in general, let's say if you have an arch and if you discretize it with 4-noded quadrilaterals, you will obviously not have a nice XY type of rectangle in your mesh. So a general element in your mesh would look something like this. So here I'm saying that node 1, if you give me the coordinates of x1, of all these 4 nodes, I need to be able to calculate all these finite element approximations, all these element matrices, and assemble them and so on. So, okay, so let me ask you this: if instead of this quadrilateral, if I had a 3-noded triangle, and if I gave you x1, y1, x2, y2, x3, y3, let's say, then how would you go about forming all those stiffness matrices and solving? So we know how to do that, right? If you give me x1, y1, x2, y2, x3, y3, we can form the element stiffness matrices. You know how to calculate the shape functions for that. But in this case, we do not actually. The question is that how do you find all these shape functions as a function of x? We know that these shape functions for the rectangle one are given right here. These are the ones that we were talking about last time. So these shape functions go to 1 at their node and 0 at every other. You can verify that all these 4 shape functions are embodied in this formula, where this C alpha and eta alpha, so these are C and eta, and if these are coordinates of +1 and -1 according to this formula. So let's take a look at this. Consider this first node. What is C alpha and eta alpha at this location? -1 and -1. So at this location, this C alpha and this eta alpha is -1 and -1. If you plug that into this formula, what you would get is 1 minus C, 1 minus eta over 4, which is right here. Is that N1 or something else? So that would be this one, right? If C and eta are both equal to -1, that would be this one right here, and 1 minus C times 1 minus eta over 4 would be this shape function right here. So why is it that, is there an error in this, in these shape functions? Does anybody have their notes from previous lectures? Right, there is, so this one needs to be here. This one needs to be here. And N2 shape function is C minus 1. So this seems okay. Now, so the N2 shape function would be does this sound correct? Does this go to 1 at this node and 0 at every other node? So if I plug in C is equal to minus 1, this will become minus 2. And if I plug in eta is equal to minus 1, then this will become minus 2, and that will give me 1 at node 1. And it will be 0 at every other node. For N2, which is this node, I need to plug in C is equal to 1, which would be here, and eta is equal to minus 1, which would be this. So the same thing we need to switch for N2 and N4. All right, so and now you can verify that these would be given by this formula. Okay. All right. So the idea is that we know what the shape functions look like on this square. We need to find out what those shape functions would be like on this quadrilateral. And we don't actually have to explicitly calculate all these shape functions. If you remember, for the three-noded triangle, we went through and calculated all those coefficients A, B, and C for the three-noded triangles. But in this case, it turns out that we don't actually have to explicitly form these functions of x and y. What we can actually do is go to a point, let's say C and eta here. So let's say this point is C eta. And all that we want to do now is to map this point to where it is actually in the real mesh. So what we also call this, we call this element the parent element, and this the real element, because this is in the real mesh. So this map is x as a vector, which has to be a function of C as a vector. So the vector x has both x and y in it. The vector C has both C and eta in it. And the reverse map will give you a function C of x. So the idea is that you should be able to make a mapping that is 1-to-1. Each and every point of this square domain, that is from -1 to +1, has to be mapped 1-to-1 with each and every point of this actual square. And this is what is called an isoparametric map. Um, so the idea here is that we are using the same to calculate the value of x. Let's say I have a point C and eta in this element. I can find out where this point is actually in the real mesh by using some sort of an interpolation over this element. And the idea is to use the exact same shape functions that we used to approximate our displacement. So if you remember, we will finally need to form these shape functions and approximate some displacement uh, over this element. So we are using the same shape functions to approximate the value of this point, which would be in the real element. This is actually x comma y. So we are using the same map that that we use for our shape functions. So what we can do is we can write this matrix. This is a x comma y as a sum of the shape functions with nodal coordinates. So the nodal coordinates are x1, y1, x2, y2, and so on. If you take the same shape function matrix that we had before for the elasticity problem, you can take this first row, multiply it with this, you will get the first row of this equation. So that would be n1 times x1, n2 times x2, and 3 times x2, and so on. The idea is that once you are given the value of c here, you can, or once you are given the nodal coordinates x1, x2, x3, x4, you can find what is the value corresponding to x by using the shape functions. So this concept is called the isoparametric map. And what does it physically look like? So if you remember, for the square element, this element goes from -1 to +1 in both the c and the eta direction. So this is node 1, which is -1 to +1. We have shape function 1 in terms of c and eta. Whereas we are going to take this shape function and we are going to map it to the real element. So we have a shape function on this domain. We are going to map that shape function onto this new domain. So essentially what we are doing is, like if you have a sheet of paper, you can stretch it and make it fit to this new domain. Either stretch it or shrink it so that it fits this new domain. And on this new domain, the same type of the value of the shape function will be exactly the same. It is 1 here at node 1 and 0 at the other 3 nodes. So if you were to go to some point, C and eta, and if you were to try to find out the value of all these 4 shape functions, it would have the exact same value at this location. So what we are doing here is let's say go to some point c and eta in this parent element. The value of the shape function 1 at that point is going to be exactly the same value here, even though this is a function of x and y. Okay, so the same sort of concept holds for both for all the 4 nodes, and essentially what we are saying is this, that this shape function for a given value of c and eta is exactly equal to the same shape function for the corresponding value of x and y. So if somebody gives you c and eta, you find where it goes to the final location x and y. If you know the value of the shape function at c and eta, that is the exactly same value at x and y. So that's the one-to-one isoparametric map that is being created from the parent element to the real element. Okay. All right. So now that we know how to use what are the shape functions on these elements, we need to find out how to calculate all these element stiffness matrices and all that. So if you remember, for the heat conduction problem, the shape function matrix was this kind of a matrix times the nodal temperatures at the 4 nodes. If I give you the nodal temperatures at the 4 nodes, you can interpolate the temperature at any point in the element using this formulation. So here's a little bit of a distinction that you have to make. This first line says that the shape function which has to be a function of x and y, and I will multiply it with these nodal temperatures. The second line says that I know that this xy is exactly equal to the corresponding C eta. So let's go to some point xy in this real element. We can find the corresponding C eta to in the parent element corresponding to that x and y. And we just said that the shape function, all the four shape functions will have the exact same value. So this and this will have the exact same value, whether it is in xy or whether it is in C eta. So we can also approximate the value of the temperature at any point in the real element with these. So the distinction is that these blue shape functions without the hat, they are the real shape functions, which are functions of x and y. These black shape functions with the hat, they are the shape functions over the parent element. Since the values are exactly the same, I can write it like this, just like in the old way, because I do not want to explicitly calculate the function for this, and I already know the function for this. So the idea is that you will use the same type of approximation for elasticity. If you remember, this was the N matrix for the elasticity matrix, for the elasticity problem, and we had 8 degrees of freedom where there are 2 degrees of freedom per node. So those are your 8 degrees of freedom. Using these, you can again calculate the displacement in the x and the y direction at any point in the real element by using the shape functions over the parent element. Okay? But the real trick comes in when you want to calculate the gradients. So to calculate the gradients, we need all these gradients because we want to form this B matrix, and this B matrix goes into the element stiffness matrix. So to calculate the gradients, what we need are derivatives. What we need are derivatives of the shape functions with respect to x and with respect to y. So all these derivatives in the B matrix, they are derivatives with respect to x, which is dn alpha over dx, not dn over alpha over dc. So what does that mean? So what it means is, if you go back to the previous page, if you go to any point in the parent domain, you can calculate what is the rate of change of that function in the C and the eta directions. So these are C and eta directions in the parent domain. That rate of change is not going to be the same in the x and the y direction. Okay? Because we have stretched and we have mapped that shape function from the C eta domain to the xy domain. So what we want for these B matrices, we want the rate of change of that function with respect to the x and the y domain, not with respect to C and eta. So to calculate all these quantities, what we'll do is use this chain rule. And after this, it is a little bit of a math, but you need to be able to follow this because you need to be able to code it later on. So we are going to use this equation to start with, and we are going to, let's say, to calculate the rate of change of the shape function on the parent domain. So this is the parent domain, this is the real domain. The rate of change of the shape function in the parent domain can be expressed with the chain rule like this, right? dn alpha over dx, dx over dc, and dn alpha over dy, dy over dc. So that if you calculate this entire term, this dc would be left in the denominator. And similarly for d eta. This is the second row. So what we are doing is we are calculating the derivatives of the shape functions with respect to C and eta on the parent domain. And if you write this out in a matrix form, what does that look like? You have this 2 cross 1 vector on the left side. You collect this term, this term, this term, this term into a matrix. And on the right side, you would have this n alpha times n alpha with respect to x and n alpha with respect to y as the vector on the right hand side. So all I've done is taken this matrix and taken those two equations and expressed in the matrix form. Um, so so what we really want in this matrix equation is this, which means that if I want to calculate this, all I need to do is take this matrix and invert it and put it on the other side. And then I will know what this vector is, because those are the two vectors that go into the B matrices, right? So these are the two vectors that go into the B matrices. So essentially what we want to do is to calculate these two vectors. And finally, how do we calculate all these, this matrix? So this was the matrix that we needed to invert. So these quantities we already know. We have the explicit expression for shape functions over the parent domain. We can take their derivatives with respect to xi and eta. These things we still have to calculate. Okay, so all these four quantities in 2 dimensions we would have to calculate like this. So this is the isoparametric map that we had introduced on the previous page. Okay, so all that we are saying here is that the location x is some function of that parent domain. So you take the parent domain shape functions, multiply them with the x coordinates of those 4 nodes, and you will get this equation, which is nothing but expanded out like this. The same thing for y. So these two equations are the same as your isoparametric map that we had just introduced. So that was right here. Right here. You take these equations, take their derivative with respect to xi. So let's take a look at one term. In this, does n alpha depend upon xi? What was the formula for n alpha? This was the formula for n alpha, right? So n alpha obviously depends upon xi, and this is the explicit expression. So this xi is a variable, this is a constant. So if you take the derivative of n alpha with respect to xi, what you would be left with is xi alpha over 4 times this term. And if you go back here, that's exactly what we have. So you can calculate dx over dxi by just taking the derivatives of this with respect to xi, and this is a constant, so it remains here. So the same thing happens for dx over d eta, dy over dxi, dy over d eta. So those are the 4 terms that we had from the previous from the matrix on the previous page. So does anybody see any similarities between this? If you collect all these 4 terms, you get this matrix J, which is called the Jacobian of the map. Has anybody seen this before, or where would that be? Where would we have seen this before? So if you remember the large deformation map that we were talking about, the deformation gradient F, that is exactly this. Instead of a deformation, now we have a map from a parent element to the real mesh. In that case, we had a deformation from the undeformed configuration to the deformed configuration. So this Jacobian matrix is the exact analog of your deformation gradient. In that deformation gradient F, you had all these types of terms. D of small x with respect to D of big X. Here you have D of x with respect to xi and eta. Okay, so if you understand, and actually this isoparametric map is much easier to follow, and you will have to follow. So if you can follow this, you can also follow large deformational problems. Okay, so at this point, there's not much to do. You just take this matrix, you can find this explicit inverse, and the rest of the steps are outlined here. These are your derivatives of the shape functions with respect to xi and eta. You calculate j, and you calculate your shape function matrices, and after that, all that you have to do is to form the element stiffness matrices. But next time we'll take a look at how do we actually calculate all these integrals. Okay. All right. So I'll see you on Wednesday.